So far with the ideas of acceleration, we have mainly focused on the way the speed is changing with time. But what if we wanted to know how far an object had traveled? This is also something we should be able to figure out based on what we know about physics so far. Earlier, we looked at a motion map for an object that was accelerating, speeding up. And we definitely saw that there's not a consistent distance between each dot. We saw that as the speed increased, the space between the dots becomes greater and greater. And this is the idea that we want to get at. We're going to develop a formula that'll allow us to figure out how far an object has moved after it's been accelerating for a certain amount of time. We actually will look at the total distance it's traveled since the beginning. We generally aren't interested in how far it goes between the 5th and 6th second or the 4th and 5th second. We want to know how far after 5 seconds of motion the object has moved overall. But we can see again that there is some sort of a pattern here. It's not as regular of a pattern, but there is one there. You may notice something from our labs that there is actually sort of a curve to these distances. Okay, just like we saw with our distance versus time graph in our lab work. It would be nice if we could just use this formula, distance equals velocity times time, but that assumes a certain value for v that we would be placing into the equation. And as we've seen, when something accelerates, it means that its value of v is changing. In this case here, it is increasing. And so which of these values would we possibly use? Well, what we actually end up needing to use is the average speed. So if you can figure out how fast on average an object is going during the time that you're interested in, you can actually determine the distance that it travels. But there's also a way of developing a formula that incorporates the value of acceleration that we've talked about before. What's most important here is the equation that's in the yellow box. But I think it's always important to know where our equations come from and that they do build off of things that we've done in the past. So when something is changing its speed, we can't just think distance equals velocity times time because the v keeps changing. But if we use our average speed instead, this formula does work out in all situations. We're going to make sure that we focus on kind of a special case where objects are starting from rest. And recall that that means that the initial velocity would be 0. That means that some of our formulas become quite a bit simpler as we work. For instance, our formula for final velocity when something is accelerating, if your initial velocity is 0, that means that you can just forget about this whole last term and just focus on the final velocity being a times t. Now let's go back to this idea that your average speed is going to be right in the middle of your beginning and your ending speed. And so it's halfway between. And if we start from 0, that means that our average speed will be exactly 1/2 of the final speed. You can see that in the diagram here. We ended with 20 meters per second as the speed. Halfway through, the speed was 10 meters per second. That is our average speed. And so we can rewrite this equation for the distance by putting in this fact that the average speed is 1/2 of the final speed. But then we can remember that for this particular situation, our final speed is actually calculated using acceleration times time. And so we can replace this part of the equation with a times t. We can use a little algebra and remember that t times t is t squared. And that's where we get this final equation. Again, what's most important is that you understand that this formula in yellow will tell you how far the object traveled, not that you can explain where exactly the formula comes from. Let's look at an example. All right, so here we have a motorcycle that is accelerating for 3 seconds. Notice again that it's moving from rest, it's starting from rest. That is going to be kind of a restriction we'll put on our problems in our class as a starting point. So we could say that the initial velocity is 0. We could also read through the problem and see that the acceleration is going to be 4 meters per second, or 4 meters per second squared, and that the time is going to be 3 seconds. Now there's actually two unknowns in this problem. What we are interested this time in is how far it has gone. So this is our question mark here. What's the distance traveled? In this case, we are not asked to find the final velocity, and so we're not going to worry about it. Let's bring up our formula that was just introduced. Distance equals 1/2 times the acceleration times the time squared. And so our distance is going to be 1/2 times our acceleration value is 4, our time value is 3, but we have to remember to square that. Now do remember from your math class that whenever you have exponents, you have to do that part of the calculation first. So the first thing I'm going to do is to take the 3 and square that and turn it into 9. And then I can go ahead and do the rest of the problem. 1/2 times 4 is 2. 2 times 9 is 18. And I was finding a distance here, so this is going to be measured in our standard unit for distance, meters. Now just to make a quick connection to something you saw before, in the lab we looked at how distance and time varied for a glider that was accelerating. And you might remember that that graph started out low and then it curved upwards like this. Well, our formula that we just found makes sense with that graph because this is a parabola. That might be a word that you are learning about in math or that you have learned about. And a parabola has a different style to its equation. It involves the x being squared. And our x is time. So that is why the t is squared in our formula.